Welcome back to statistics. In doing inference for a categorical variable like presidential approval or something like who you plan to vote for in the election or your opinions on almost anything, the typical thing we're interested in is the fraction of folks, the fraction of individuals who fall into each possible category. So, for instance, in a presidential approval poll, maybe the question is, do you approve of the job the president is doing? And typically, respondents will be given a sort of preset menu of answers. They may, for instance, be allowed to say they strongly approve, they approve, they're neutral, they disapprove, or they strongly disapprove. So that would be like 5 different categories that an individual could respond with. And what we're interested in is the fraction of the population that answers in a particular category. So, for instance, the fraction of the population who strongly approve, the fraction of the population who are neutral or undecided, and so on. And so, we use the methods of confidence intervals to estimate those proportions, and there are also significance tests you can do for those proportions. We can also compare the proportions between different groups. So, for instance, I may be interested in looking at the president's approval rating among men and women, and I may be have the idea that for some reason the president's approval rating among men may be greater than his approval rating among women. Questions like that are questions about comparing two proportions. And in this video, we'd like to talk about the statistical methods for making those kind of comparisons. So let's take a look. Comparing two proportions. I'd like to, as usual, sort of unveil the theory in the context of an example. And the example here is the response is between two different groups, high school students and high school teachers, to a question about student journalism. The question you see here is, should students be allowed to report controversial issues in their student newspapers without the approval of school authorities? So this question was asked to a sample from each of our groups. A sample of 10,000 high school students was asked this question, and a sample of 8,000 high school teachers was asked the same question. And the results were interesting. Of the 10,000 students, 5,823 of them responded yes, students should be allowed to report controversial issues without prior approval. But of the 8,000 high school teachers, only 3,125 answered yes. And so we see that more than half of the students thought that student journalism should be unfettered by any sort of requirement for approval, while less than half of the teachers thought the same thing. So, what we'd be interested in here is comparing the true proportions of high school students versus high school teachers who would respond yes to our question, right? We'd want to estimate in particular the difference between those proportions. Let's say student minus teachers of the in the two groups who approve of sort of this unfettered student journalism. So the outlines of our problem are similar to the outlines of any two proportion problem like this. That is, there's going to be two independent populations. Those would be the students and the teachers in our example. And from those populations, you draw two independent samples, one from each group. That would be our 10,000 high school students who responded and the 8,000 high school teachers. The statistical variable in play here we could call agreement with freedom of speech in student journalism, right? It's a categorical variable, and there were three levels to it, three values. Responses were either going to be yes, I do think students should be able to publish these controversial pieces without approval. No, I don't think they should be able to. And respondents were also allowed to have a I'm not sure response. And what we'd like to do is estimate the true difference in proportions between each group who responds yes. And by true here, I mean population. We want to estimate the true population difference in proportions between teachers and students in responding to this question. The notation and terminology we use is going to be very similar to the notation and terminology for one proportion problems. So we'll still use the letter P to denote the population proportions, but we'll have a subscript, either P1 or P2, to let us know which group we're talking about. So P1 would be the true population proportion in group 1, P2 would be the true population proportion in group 2. And these are population parameters, right? So they're typically unknown. The sample proportions are going to be denoted by p hat again. And again, we'll have a subscript telling us which group we're talking about. These are sample statistics, and so we're going to need to investigate how these sample statistics vary from sample to sample in order to do our inference. The sample counts of successes will also be denoted similarly by an X. X1 is the sample count of successes in group 1, X2 the sample count in group 2. And again, by a success, we simply mean, an observation is a success if it falls into whatever category we're interested in. In our case, we're interested in the category of those who answered yes to our question. Students should be allowed to publish without a prior approval. And so that would be a success. An individual who answers yes in our situation would be a success. The parameter of interest that we're going to study is the difference in population proportions between group 1 and group 2. And pretty naturally, I think our point estimate for that difference is going to be the difference in sample proportions. That's the best information we have about the proportions in each group coming from our sample data. The point estimate, is a sample statistic, so it varies from sample to sample, and we're going to need to know about the sampling distribution of our point estimate. The first fact to understand is that it, like pretty much all of our point estimates up to this point, is an unbiased estimator of the parameter of interest. That means that the mean of our point estimate, the mean value of P1 hat minus P2 hat, is equal to the difference P1 minus P2 of our true population proportions. We also need to know about the standard deviation of our point estimate, and that's given by this formula here. This formula comes from the probability theory, and you'll notice that it involves the population parameters P1 and P2. Since those are unknown, we're going to have to estimate our standard deviation for our point estimate using a standard error. And the standard error, as usual, is obtained by simply replacing the unknown population parameter, P1 and P2 in this case, by their associated sample statistics. So we estimate P1 by P1 hat, we estimate P2 by P2 hat, and making those substitutions gives us the standard error of our point estimate. So again, we think of the standard error as just our best estimate for the standard deviation of the point estimate. Finally, we need to talk about the shape of the sampling distribution. And again, the story is familiar here. That shape is approximately normal, and it gets increasingly more normal as the sample sizes get larger. So we know the mean, the standard deviation, and the shape of the sampling distribution now. And we have to ask the question, well, okay, when is this normal approximation accurate enough to use in our inference procedures? And the answer here is sort of similar to the answer for a single proportion. You'll recall that for a single proportion, the normal approximation is accurate as long as you have at least 10 successes and 10 failures in your observations, in your sample. In a two sample problem, you need that to hold for both samples. So we need at least 10 successes and 10 failures in each group. And clearly we have that in the example we've been considering, right? Out of our 10,000 students, over 5,000 of them were successes. They answered yes. And that would mean that, somewhere between 4 and 5,000 responses were also no. There were at least 10 successes and failures in the student group. And by the same token, since there were 3,125 successes in the teacher group of 8,000, there's clearly going to be, 8,000 minus 3,125, which is at least 10 failures in the teacher group as well. So we certainly satisfy the conditions for inference that are necessary to use the normal approximation here. Just as an aside, if those conditions aren't met, there are other procedures we can use, and we'll in fact have time to talk about this a little bit later in our course. So once we have the sampling distribution for our parameter of interest, we're ready to form a confidence interval. And as usual, our confidence interval is going to be our point estimate plus or minus a margin of error. So we have P1 hat minus P2 hat, that's our point estimate, plus or minus our margin of error, M. And the margin of error is a critical value from the standard normal distribution times our standard error. This is, again, completely in line with the margins of error we've computed in other situations. So that should all be very familiar. So how does this work out in our example? Well, let's use that theory to form a confidence interval for the difference in proportion, students minus teachers, in the populations of all students and high school teachers in the U.S. So our point estimate for P1 minus P2 is going to be P1 hat minus P2 hat. And that's just our ratio of sample counts to sample sizes in each group. So that winds up being, that difference in sample proportions winds up being 0.1917 to 4 places, or about 19.17%. Our critical value for 95% confidence comes from the standard normal distribution, and we've seen this particular confidence level so often you probably just remember that it's 1.96, but you would find this using software just by looking at the upper bound of the middle 95% of the standard normal distribution. So we have Z star as 1.96. Our standard error is computed according to that sort of beastly formula we saw a few slides ago, and there it is. You need to be kind of careful in computing that just to make sure all the operations are done correctly. And so just take care in making that calculation with your calculator. You basically want to work from inside out. Compute the first fraction, compute the second fraction, add them, and then take the square root. Now that we've got a critical value and a margin of error, and a standard error, we're able to compute the margin of error. The margin of error is the product of our critical value and the standard error. So we have 1.96 times our 0.007354. That gives us a margin of error of 0.01441. Therefore, the 95% confidence interval is going to be our point estimate. That was our difference in sample means. That was 0.1917, plus or minus our margin of error of 0.01441. And that turns out to extend from about 0.1773 up to 0.2061. And so we're 95% confident that the true proportion of students who favor reporting controversial issues without school approval is between 17.73 and 20.61% higher than the proportion of teachers who favor this. Right, because that interval from 17.73 up to 20.61 is the confidence interval for the true difference in proportions. That difference, P1 minus P2, you can think of as how much more P1 is than P2. So we see that the procedures differ in their details, but in overall outline are very similar for a two proportion problem. And we can put another notch in our belts. We now have inference procedures for uh, two proportions, for one proportion, for two means, and for a single mean. And so we're building up a pretty healthy toolkit here for statistical inference. We will have more to say about inference going forward. In the meantime, take care, stay safe, and we'll talk to you again soon.